My name is Kapil Karkra. I am a senior principal engineer at Solidigm, and I'm the lead software architect of the cloud storage acceleration layer. The title of my presentation is New Developments in Cloud Storage Acceleration Layer in FTL in SPDK. So imagine if we had a sandbox to which you could add capabilities and drive down the TCO. The new capabilities could be the SSD level capabilities. They could be the software level capabilities or platform level capabilities. You may make them open source or closed source. And this right-hand side chart, I'm showing a dual y-axis chart where one would add these new capabilities as vertical bars, and the TCO would go down as shown by the yellow line going down. So hold on to this part about the sandbox, and we'll get back to it. But let's review our agenda here. So we'll first talk about the TCO benefits of Solidigm's recently launched hyperdense 61.44 terabyte QLC. And really the motivating problem for storage developers is how to expand the reach of this QLC to more customers and more use cases. And the solution to the problem is to create an easy button with cloud storage acceleration layer and the reference storage platform, what I'm calling the sandbox, and you will see shortly. We will share some performance and TCO numbers that we collected by putting Solidigm's drives with CSAL inside this sandbox. And finally, we'll summarize and leave you with a call to action. So let's look at the in detail, the motivation and problem first. So a wide range of use cases and customers are adopting QLC. And one example that I jointly presented with Alibaba at last year's SDC was this Alibaba local disk use case. You can get more details in that presentation. I have included a link to that presentation at the end of this presentation. But let me briefly recap what this use case is. So Alibaba replaced their HDDs with QLC in their third generation big data local disk instances to double the performance and density. So they doubled both performance and density, so net 4x benefit. And this essentially enabled them to hold the price of their third generation local disk service constant, basically same price as the second gen HDD based local disk instances. But the performance doubled. To make it simple, an iPhone analogy comes to mind. So the new iPhone came out last week. It is the same price as the last year's iPhone, but the performance is much better. Alibaba basically delivered the same thing to their customers with their local disk service. So they doubled the performance of their third gen QLC-based big data instances, but held the price of those big data instances same at what they had in the second generation with HDDs. So there are two things that we got from this deeper collaboration with Alibaba. One, it was a great use case for QLC replacing HDDs. And second, we co-developed this cloud storage acceleration layer with them. But Alibaba's use case, this local disk use case, uses Optane SSDs as the write buffer cached here in front of the QLC. It is an O plus Q use case, Optane plus QLC use case. As we talk about extending the QLC's reach, especially for O plus Q deployments like Alibaba's local disk use case going forward, as we know, Optane is done. So we must have an Optane SSD's replacement. And Solidigm has engineered its P5810 SLC SSD to replace P5800X for O plus Q deployments. Based on the empirical field data on CDN and big data workloads and many internal analyses, we projected the worst case endurance demand to be about 37 drive writes per day. Optane was supplying 100 drive writes per day. So we designed P5810 to provide 50 drive writes per day. Another main goal of Optane in O plus Q deployments is to eliminate these small write penalties. So random 4K write performance is crucial. The typical CSP deployments we have seen throttle at about 8,000 IOPS per virtual drive, and P5810 matches that pretty well. So the requirement is about 8K, and SLC delivers about 10K. Note that in this example, single instance of CSAL runs on a single vCPU and binds to a O plus Q or Optane plus QLC pair, exposing 8 virtual disks. So these performance numbers are the performance line, the random 4K performance line is especially for a single virtual disk. So you have to multiply it by 8. And also note that the workload is a uniform random 4K write workload on top of the CSAL. Underneath the CSAL is utilizing Optane bandwidth for various flows. For example, all writes land on Optane sequentially and are later read from Optane and written to QLC sequentially with optimal write side. So the workload is a complex mix of reads and writes, sequential and random. But the dominant flow is the management of paged logical to physical mapping table, where CSAL must frequently page in and out 4K pages randomly, as CSAL keeps only a small portion of its L2P in DRAM and saves the DRAM costs by putting the actual copy of the L2P table on the SLC partition. So no doubt, P5800X delivered great performance. I worked on Optane technology. I'm still sad that it is gone, but I'm happy that at Solidigm we have taken the learnings from P5800X and O plus Q use cases to create P5810 that provides a better cost performance endurance fit to O plus Q use cases. So, all right. So with the launch of our 61.44 terabyte hyperdense QLC that is now 4x denser than the previous P5316 QLC drive that Alibaba deployed in their O plus Q local disk use case, and with P5810 SLC replacing Optane, even greater TCO benefits are now possible. In the table here, what I'm showing is the O plus Q is on the left-hand side, and S plus hyperdense Q, this SLC plus hyperdense QLC on the right-hand side. And you can see when we account for all the CapEx, OpEx, rack tax, all the TCO numbers, we basically see about 2.5x benefit of S plus hyperdense Q over O plus Q. So to give you a sense for this, if we express the 5-year amortized cost of storage node, including CapEx, OpEx, and rack tax, into a single dollar per gigabyte number, and these numbers will obviously vary, it's somewhat hypothetical, but so if you spend 20 cents a gigabyte on O plus Q box, that's a local disk box, let's say you're building storage, with hyperdense QLC and P5810 SLC, you will only need to spend 8 cents a gigabyte. That's 2.5x difference, right? So 8 cents to 20 cents per gigabyte becomes 8 cents per gigabyte. This is huge TCO advantage of hyperdense QLC. So hyperscalers and large customers already know how to take advantage of these TCO benefits and are rapidly heading down this path to make necessary changes to their software stacks. Again, the motivating problem for us storage developers is how we can bring these advantages of hyperdense QLC to everyone, not just the large customers and hyperscalers, but everyone. CSAL is part of the answer. So I've divided the solution portion into two distinct sections. First, we'll talk about CSAL, Cloud Storage Acceleration Layer, and then we'll talk about the reference storage platform. So let's jump into the CSAL a little bit more. So this is definitely, for those who missed the last year's presentation on CSAL at SDC 2022, here's a refresher for you. CSAL is a host-based FTL in SPDK. It's a BDEV in SPDK. And let me explain what it does with a performance pipe metaphor first at a high level. You know how NAND has a read pipe that's yay big, quite big. QLC read pipe is as big as TLC read pipe pretty much. But the write pipe is narrower in NAND in general, but then QLC has even narrower write pipe. So what CSAL does is it tries to make the write pipe bigger along with reducing the TCO. So how does it do that? It does that by write shaping. So it uses a tiered architecture where SLC acts as a persistent cache or write buffer, here fronting the large pool of hyperdense QLC. All writes land on SLC. Any short lifetime data gets deleted in SLC itself and never needs to be moved to QLC. And CSAL writes the long lifetime data. It reads from SLC and writes to QLC sequentially in optimal write sizes in a very NAND-friendly manner. So CSAL also places its paged logical to physical mapping table on a partition of this same SLC drive. And in this table shows how CSAL uses SLC. It uses the cache region, which is obviously the write buffer portion, but also the L2P region for paging in and paging out the logical to physical mapping table. And then finally, it stores its own metadata. CSAL is an FTL, it's crash consistent, power fail safe FTL. And so we keep our metadata on also a portion of the SLC. Let's quickly look at what changed in CSAL since the last SDC. So first, we open sourced CSAL in SPDK version 22.09. And then in February of 2023, Solidigm acquired us. As Intel wound down Optane business, it also decided to end of life CSAL. And for Solidigm, it was crucial for our relationship with Alibaba and for QLC. So Solidigm acquired us. And one of the first things we did when we joined Solidigm was to work on establishing SLC product that we were working on, P5810, as a replacement for Optane for O plus Q use cases. And one of the things we also did is CSAL relied on Optane providing the VSS capability for power fail safety and consistency. Our algorithms depended on VSS capability from Optane SSDs. And one of the first things we did, we changed the CSAL algorithms, power fail safety and crash consistency, to not rely on VSS. And this simplified our SLC implementation because we didn't want to put that complexity of implementing VSS in SLC. So we changed CSAL instead. And all the patches for this capability are available. CSAL works. CSAL is crash consistent, power fail safe still, but doesn't need VSS capability on SLC drives. We are also working on RAID 5F and our ZNS and FTP readiness in CSAL is in progress. Let's look at CSAL's new capabilities in a bit more detail. The first capability we've already talked about, the need for CSAL write shaping for both large IU and emerging interfaces like ZNS and FTP. In addition, the locality-based workloads can see 2x more performance and endurance benefits with CSAL's tiered approach. So here in the table, you see a 64K random write workload. It's a Zipfian workload with a theta of 1.2 that roughly maps to about 95% of the accesses are to 5% of the LBs. It's highly temporal locality-oriented workload, very cache-friendly. Most of the writes are dying in SLC itself. So you see basically SLC performance predominantly, and therefore you see 2x benefit over TLC in this case. So yeah, caching definitely, CSAL tiered approach will benefit if you have caching-friendly workload. The capability number 2 is the RAID 5F or full stripe RAID 5 capability. So as you guys know, the ZNS and FTP both have these configurations that basically make it very hard for SSD to implement XOR. And so once we drop XOR for those configurations from SSDs, we drop reliability as well. So CSAL picks that reliability back up by implementing RAID. But the the RAID 5F that CSAL is implementing is very efficient. It's 2 to 3x more efficient compared to the traditional RAID 5, because we have this SLC tier that always can play, that can always play the full stripes to the RAID 5 DDAV. And RAID 5 implementation also tremendously simplifies, because we only ever have to implement a full stripe RAID 5. And we are able to, again, do it because we have SLC tier, persistent SLC tier from where we can play the full stripes. Also, the parity RAIDs have this problem of write hole. And to close the write hole, you have to log additional writes. And if you see this, just formula, based on formulae here, full stripe RAID 5 is 2x better than read modified RAID 5. And then in addition, you don't have to close RAID write hole, because we have that SLC tier. We can always replay. If dirty shutdown or power failure were to occur, we can always replay the data from the SLC tier again. So 2 to 3x more efficient RAID. Basically, RAID 5F performs very much like RAID 0. All right, so capability number 3 is this pooling. So CSAL and SPDK offer a ton of flexibility in terms of how we pool QLC capacity. And pooling helps with sharing and increasing capacity and performance utilizations of these large SSDs. Obviously, if you plugged in a 61 terabyte SSD in a single node, compute node, you can't use that capacity and performance, and especially capacity and pooling, disaggregating. You will see there's a case study coming up here in this presentation, disaggregation case study, and that's the perfect way to improve the performance and capacity utilizations of these large SSDs. And this slide on the right-hand side came from our Western Digital friends, Matthias and Dennis. They presented this slide at various conferences. They use CSAL to adapt ZNS to 4K block interface. And the table below shows how CSAL can prevent different workloads from mixing and blending together to achieve a WAF optimization. In this case, WAF goes down from 3.8 on a conventional SSD that has mixing going on and blender effect going on with all these different lifetime data and streams mixing, to basically 2.3, because CSAL can trivially do the multi-tenant isolation and achieve that WAF when the backend is something like a ZNS drive. And it can achieve this trivially because you can think of like SSD, a large pool is divided up into different LBA partitions, and user LBA, we can look at the user LBA, say which partition assigned to which tenant, and we can, at the back end, just assign or steer the LBA partition based on LBA partitions, the tenant's information to its own set of zones to kind of get that tenant isolation very trivially. Okay, so to summarize, CSAL is building all the key abstractions to extend the use of hyperdense QLC and adapt the emerging interfaces to 4K block interface. So because we are adapting to FDP and ZNS and large IU drives, applications on top of CSAL can continue to be unaware of those technologies, can continue to use good old 4K block interface and don't need to change. So what else is CSAL doing? What else is Solidigm doing beyond CSAL? We're taking the next step in our solutions-based approach to create a reference storage platform. So now we're heading into the sandbox part of my talk. So why reference storage platform and why a community-driven approach? First, open source building blocks are a bag of parts that are hard to put together. It takes a lot of geeks to do that, and we're like geeks like us, we still run into a ton of issues. So this hampers rapid development, assessment, and deployment of storage technologies. The reference storage platform brings it all together into a turnkey solution. A car analogy comes to mind. As SSD vendors, we're building a tire, but I want to know, when I fit this tire into a full solution like a car, what kind of performance and TCO benefits I'm bringing to the solution, the car, at the car level or the solution level. I don't have this kind of solution available readily today to do that. And the reference storage platform provides precisely that. Community-driven approach enables faster innovation, transparency, easy evaluation, and adoption of these part technologies into a unified whole. And these part technologies don't have to be only SSD level technologies. On the right-hand side, I'm showing the chart where over time, we can build capabilities and bring a solution level TCO down. So for example, as SSD vendor, as an SSD vendor, we can bring new technologies like our hyperdense QLC, ZNS or FDP SSDs and test these part technologies benefits at the solution level. But then software guys can test their RAID, compression, bunch of other algorithms into this solution and see what kind of benefits they get at that solution level. And reference storage platform is also great for platform level capabilities like IPUs. For example, you can build your storage node with IPUs instead of x86 nodes, x86 based servers. Finally, you can build your own differentiating capabilities that you may not want to open source. In fact, one of our partners, Starwind, does exactly this. They take all the open source parts of this reference storage platform and add their HA capability on top. They won't open source that piece. That's their secret sauce, the HA piece. And that is cool. Now, the good news is that the first instantiation of this is already done and available today. Thanks to our reference storage platform partners, we have created the first instantiation of open source reference storage platform, and it is the SPDK NVMe-oF Fabric TCP target for disaggregation use case. How is this providing an easy button? So we have an NVMe-oF Fabric TCP target packaged into a turnkey container and a turnkey VM image. And we have a GUI to manage a pool of NAND. You can create a pool of hyperdense QLC, compose storage volumes of various sizes, expose them out of this NVMe-oF Fabric target to multiple and assign them to multiple cloud tenants. All this works. You can pull these images as easy as pulling down these images to some our defined reference hardware platforms. And they are commodity servers from standard OEMs with Intel CPUs. We have picked Dell and Supermicro servers. Now, detailed getting started guides and full documentation is available on spdk.io and Solidym's website. I have the links at the end of this presentation for both of those. And you can also build your own container or VM image if you wanted to customize to your hardware, to other changes, you could do that. We have a step-by-step instructions for doing that. And so next, in keeping with the ethos of eating our own dog food, Solidigm used this reference storage platform to illustrate the performance and TCO benefit of our hyperdense 61.44 terabyte drive, along with our P5810 SLC drive. So let's look at these performance and TCO benefits. Okay, so I've set it up as a disaggregated use case, and we have A/B comparison set up as an A/B comparison. The table shows our A/B performance comparison on a single socket server with 10 PCI Gen 4 slots. We use 10 TLC drives of 16 terabyte capacity. These are P5520 drives from Solidigm. And compare that with CSAL configuration where we have paired 7 of our 61 terabyte QLC 61.44 terabyte QLC drives with 3 800 gigabyte P5810 SLC drives. So 3 SLC and 7 QLC. And we can immediately see the density difference between the two columns. TLC can provide only 138 terabyte, while QLC gives 344 terabyte, 2.5x more density. This is a disaggregated NVMe Fabric target where we are composing 16 terabyte virtual drives. So size of the virtual drives is 16 terabyte, and each virtual drive of 16 terabyte is capable of delivering 500 megabytes per second per virtual drive. And the chart below the table shows how a 100 gigabit Ethernet network, we can disaggregate all of 344 terabyte capacity to give 21 virtual drive units as performance units, whereas the TLC can only get like about 8. such performance units because TLC lacks density. That's the power of density. 2.5x more virtual drives you can create, 16 terabyte each you can create on the higher density box compared to the lower density box. At higher networking speeds, obviously, you can disaggregate more capacity and achieve higher performance SLAs, not just 500 megabytes per second per virtual drive. Now, just wanted to quickly say that we are saturating 80% of the 100 gigabit Ethernet here. And TLC may deliver more performance, but that performance is going to get left on the table because your SLA demand is only 500 megabytes per second per virtual drive. So QLC is able to meet that demand. And you are going to be ultimately saturating, the bottleneck would be network here, 100 gigabit Ethernet network. So on the TCO, now TCO includes the CapEx, OpEx, and all of the data center tax components here. You know how TCO works on TLC side because there are only 8 virtual drives, while on the right-hand side with QLC, you have 21. To reach the parity in terms of capacity, you have to pick up non-storage BOM and boxes by having 2.5x more TLC boxes to reach the capacity parity. And this leads to basically 35% of TCO benefit of using S plus Q configuration with CSAL. Conservatively speaking, we have seen easily up to 50% benefits, and 50% TCO advantage means you're cutting your TCO down in half, or 2x TCO advantage, so to speak. So in summary, you can think of this, think of the whole thing this way. NVMe over Fabric's target is the big drive of the data center. And this drive is 80% saturated in terms of bandwidth in both cases, TLC and QLC. There's a 100 gig Ethernet in the front end of this big drive, and both are saturating it at 80% of the bandwidth saturation. But the QLC side is achieving that with 35% lower TCO based on density alone. That's an important point, based on density alone. And you know how we talked about adding other capabilities to both reference storage platform and CSAL to bring the solution level TCO down. So we definitely have roadmaps for both CSAL swim lane and reference storage platform swim lane, where we talked about ZNS and FDP, we're adding RAID, and we're adding multi-tenancy and costs. All of these things can basically bring down the TCO. And again, on the RSP swim lane, we are reference storage platform swim lane, we are adding more use cases, more platforms, more architectures like IPUs, etc. Let's summarize. First, Solidym's P5810 provides optimal balance of cost, performance, and endurance. It provides a great fit for O plus Q use cases, better than Optane in terms of cost. CSAL has all the necessary abstractions you need for the emerging SSD interfaces like ZNS and FTP and large IU, etc., with high density NAND. We have provided turnkey open source disaggregated NVMe-oF TCP target as our first instantiation of the reference storage platform, and it is, along with CSAL, the reference storage platform provide easy buttons to adopt new technologies. Continuing technology additions, like I showed in the previous chart, and I said that before, as you add more additions, platform players, software players, SSD vendors, all these horizontal players can add their pieces to this reference storage platform, use this reference storage platform, and continuing additions as we expand this drives the TCO down at the solution level. So call to action. So how can you engage with us? So first, you can be a developer with us, developer of CSAL with us in the SPDK community. So that's the primary way you can interface with us for both reference storage platform and for CSAL. Use the NVMe Fabric target we have provided to see the great things it can do for you. And you can add your own capabilities and create more reference implementations with us. Let's grow this community for the benefit of the entire storage industry. We invite you to play with us in the sandbox here. That concludes my talk. Thank you.